Hi, I'm Yash, and I'll be talking about our work, Invertible Neural Skinning. We consider the reposing task in which, given raw scans and SMPL-fitted poses of a subject, we wish to construct an animatable representation of this person. To construct this representation, we first define a canonical space where the subject pose is fixed, and then we encode the subject in this space using an occupancy network. To animate this implicit representation, we can use linear blend skinning, which is a way to animate 3D surfaces based on relative bone configuration, from the canonical to the deformed space. In linear blend skinning, for every point Vi on the surface, we define a set of weights Wij that define how much the jth bone contributes to the movement of this point. These weights define how much each bone movement contributes to the motion of a given point, and all the weights for an individual point sum to 1. To use LBS, we learn an extra MLP that predicts LBS weights for every point. However, since LBS is only a linear combination of bone transforms, it cannot really capture the nonlinear deformations of clothes and body tissue. This can be seen in the visual below. To overcome this, prior work, such as SNARF, conditioned the canonical representation on the target pose. Seen in the visual, this leads to better results but come at the cost of two major drawbacks. First, at each time step, we require a separate mesh extraction pass of the occupancy network, which is time consuming. And second, there are no correspondences that are preserved between the mesh of the same character across two different poses. Our core contribution is the use of invertible neural network in the reposing pipeline. An invertible neural network, or INN, defines a bijective mapping between its input and output spaces. And in our work, we use INN to deform points in 3D space. Our first contribution is introduction of a post-conditioned INN module, which handles nonlinear deformations such as those of clothes that are caused due to the pose change between the canonical and deformed space. Our second contribution is the bone pose encoder. We encode each bone pose separately using a shallow MLP and concatenate it to get the body pose embedding. We take a dot product of this pose embedding with the spatial embedding, which ensures that the deformations caused by the INN only occur when the pose embedding is non-zero. For more details, please refer to our paper. Using this bone pose encoder, we build the post-conditioned INN and use it to model nonlinear deformations. We chain two post-conditioned INNs around a LBS block to build the final reposing pipeline. Training, we sample the points in the deformed space and train our network to predict its occupancy value, 0 or 1, using the binary cross entropy loss. Whereas during inference, we first extract a mesh in the canonical space exactly once, and we repose it using the learned LBS module and the post-conditioned INNs. In previous work, we report two metrics, bounding box IOU, which tells us how many points sampled uniformly in the space have correct occupancy, and the surface IOU, which tells us how many points sampled around the ground truth surface have correct occupancy. We find that using INS, we can match or outperform all the previous methods and baselines on both our metrics on the closed human dataset. Since INS requires mesh extraction at only the first step, it is also an order of magnitude faster than the baseline SNARF. In our ablation study, we found that not using the bone close multiplication led to a huge drop in performance. This allows us to preserve surface correspondences. We can propagate mesh attributes such as texture using it. This is a visual example displaying the same. On the other hand, Previous methods such as NARF do not display these benefits.
In this visual, we demonstrate the post-conditioned variations introduced by invertible neural scanning module.
In summary, we discussed about invertible neural scanning, an end-to-end learnable reposing technique that preserves surface correspondences, is more accurate and captures post-varying effects, and is also an order of magnitude faster than state-of-the-art. Thanks for listening.
To find out more about INS, please visit our poster on Thursday morning at CVPR.